Hello students, welcome back to the next lecture on classical electrodynamics, and today's lecture is lecture number 15. In the previous lecture, namely lecture number 14, we have seen the definition for the linear dielectric, and when the linear dielectric is also considered to be homogeneous, and the classification of the dielectric into isotropic and anisotropic dielectrics. So these are the topics that we have seen in the last class, and even before to the previous class we have seen what is meant by dielectric polarization and how to understand the dielectric polarization in terms of certain charge densities present inside the dielectric. We have seen this particular topic with a considerable introduction in the last class, and therefore today we are not going to see the introduction. So let me therefore show the place in the board where we have discussed the classification of dielectrics, and then we have seen the definition for the linear, non-linear, as well as the isotropic and anisotropic classification, and what is the meaning of the susceptibility tensor, etc. And I also explained how this kind of study has led to the development of new fields such as nonlinear optics and discovery of the new materials such as what you call the functional materials such as the ferroelectric materials. Okay, so these are the advancements in the study of the dielectric polarization in the materials, and therefore these become the specialization where you take up a project or do your doctoral work. So coming to the usual coursework on the MSc level, we are therefore proceeding further to the case of linear dielectrics only. So the point is therefore clear that rather than going to the special topics such as nonlinear and anisotropic situation, the most general situation to study would be the linear dielectrics. So linear, homogeneous, isotropic is the one that we would like to do, and therefore I will write down that our study will be therefore focused on linear, homogeneous, and isotropic dielectric. So that is what I would like to stress now in this particular lecture, and we are interested in today's class to obtain the relation between charge densities. So even though we have seen the classification, remember linear, homogeneous, isotropic, LHA dielectrics only we will be considering in the coursework, or that means within your syllabus. So corresponding to this linear, homogeneous, isotropic situation, what would be the equation for the polarization? That's what we have seen in the last class. So this is the linear relation corresponding to the isotropic case, and from which I can write down the electric field as, you just rearrange P divided by epsilon naught into chi e. That's all about it. And we are trying to obtain some relation between the we are interested to get the relation between the two types of bound charge densities. That is your aim. So let me make the aim clear. I'll write down what is the purpose of the today's classwork. We are interested to find out how the dielectric constant, that is epsilon r, is related to the bound charge densities. There are two types of bound charge densities are there. So this is our aim. So the purpose of the today's class is to find out the relation between epsilon r and the two types of bound charge densities. So therefore let us start with the Gauss law in presence of dielectrics. That's what I have written there. And therefore you can now expand and write epsilon naught epsilon r into divergence of. Now what is this d actually? This is what you'll have to write down, that you write this expression as P divided by epsilon naught into chi e. That is equal to rho free. So this is clear, right? So you can see that d, first of all you'll have to write down that d as, d should be written down as epsilon 0 epsilon r into e. That's what is d. That e is there inside. Okay, that electric field is now we are going to write down in terms of the polarization. That's what I have written here. So d equal to epsilon e, that is first step. In that you are going to substitute capital E equal to this much. That's what I have written. And once this is clear, now we can think about what is this divergence of P, because anyway this is a constant, it will come out. And therefore the divergence of the P we have already established in I think 2-3 lectures before this one. Probably you verify in lecture number 11 we have calculated what is the divergence of P. So we are going to substitute that value for the divergence of P. So in particular, you know what is that? I will write down that divergence of P is equal to minus of the rho bound, that is the volume charge density. This expression is derived expression. So we are going to substitute that right now. And you should also remember, whenever any other expression comes, we'll have to substitute. So there is a chi e here. So probably you should remember that 1 plus chi e equal to epsilon r. This one we have derived in the last class. Okay. So therefore, if you substitute all these things, I get like this. There is a there is a into, right? Epsilon r divided by epsilon into multiplied by, you have minus rho b. Rho b means bound, and that's all. That is equal to rho f. So instead of writing free, I will write only f here. So that gives you epsilon minus, let us write down minus epsilon r by epsilon r minus 1. And that's all about it. That is equal to, we can write down rho free, then we have divided by rho bound. I think that's all. We cannot do much simplification to this. So let me therefore highlight this result. So this is one of the important results when you are performing some problem like solving numerical problem or whatever it is. This relation is very important. So let us call this as a first relation. Why I am trying to explain this is that you are going to have, see here you have two types of charge densities are there. Okay, so you have the two types of charge densities. One is free and other is bound, but that is one thing. Second thing is you also have sigma. So this is rho. So I would like to emphasize that. So I will write down that in our title we have. So what is our title? Let us go back and verify. In the title I have written bound charge densities, right? So that bound charge density, you should always remember that there are two types are there. So I would like to say that one is the volume bound charge density and another one is sigma, that is the surface charge density. We need the relation for both of them. So right now what we have calculated is only for the rho bound. That is a point to be noted. So that is why I am saying that it is result 1. So let us therefore discuss how to obtain the connection for the surface charge density. So I'll write down. Similarly, we can do something. So similarly, let us use another relation. So if we are going to use another relation, what is the relation that already you know? It is the normal component of the polarization is equal to the sigma bound. So this is the equation that you are going to use. This equation is already known to you, like I think lecture number 11 you verify, we have derived this. So we are going to use this particular expression together with whatever definition that you know from the last class. Okay, we have some definitions in the last class. So what are the definitions? So just recall and then let us substitute that. The definition for the dielectric, what is that called? A displacement vector. I am talking about the D vector is epsilon naught E plus P. So this will give you information about the polarization. So the polarization is given by the displacement vector minus epsilon naught into E. That is one relation. But you also have a similar relation for D. So let me write down that the D vector is equal to, because it's another relation, I will choose another color, epsilon into E. So these are the relation that we have seen from the last class. And we are going to manipulate these two relations in now. So let us manipulate now. So let us come to the normal component of the polarization. So we'll come here now and then substitute P dot n equal to sigma b. So therefore now we are ready to substitute all the expressions. So what is the P here that you are going to substitute? This is what you have to substitute here. So D minus epsilon naught into E is it correct? So we are going to use both of them, that is equal to sigma b. Yeah, that's okay. So we are going to use this expression D by epsilon here and this is epsilon naught into E. So both of the relations we are going to substitute here so that we are getting the relation like that. And once that is fine, and now we can proceed. Equal to sigma b, but what happened to the, but there is a dot n, right? See, there is a dot n, I missed it, right? So let me put the dot n. So that has to be inside the bracket. Then you put a dot n, then that is equal to sigma b. So the dot n is what I forgot. Okay, each one of them is also vector quantity. And that's all about it. And now we can take something common. So let us take d common. If I take d common, I get epsilon r minus 1, then divided by epsilon r, and that's all. Then you get a d dot n, and that is equal to sigma b. So typically you can't do much more simplification, and that's all about it. So let me therefore say that this is the required result. But there is a point to be noted, we can simplify, but now we cannot do. I need to explain you what is meant by d dot n. Okay, if you know that, then only you can simplify. So therefore, for the time being, I will write it as the second result. But this equation cannot be simplified without knowing what is d dot n. So let us therefore understand what is the normal component of the d vector. Of course, meaning is clear. D dot n means the normal component of the what is the d displacement vector. Okay, but however, the meaning is that where this particular normal component will come is naturally it will come at the interface. Interface means where the boundary is there. That is natural, right? This is connected to the surface charge density, right? So because it is connected to the surface charge density, the normal component of the D has to be found out at the surface of the dielectric material. So ultimately, what I'm trying to explain you is that if you know the value of the d dot n, that's what we are trying to say. Okay, can we evaluate, or if we can know this particular expression, namely d dot n, I'm talking about the d dot n. So this one I'm interested to evaluate. So let me write down this d dot n. So can we evaluate d? No, that is not d yet, right? Okay, dot n. So that is the question. Can we evaluate that? Now, to evaluate this, we have to understand a little better. So the point to be noted is that the evaluation comes at the surface of the dielectric. That's important. Okay, you can understand what is surface. Surface means boundary of the dielectric material. Okay, boundary of the dielectric material. Then only surface will come. Therefore, before simplifying, or before we can understand, so there is a point to be noted that in the result 2, this expression can be simplified only if you know something about d dot n. Therefore, we have the next work to be evaluated is the d dot n. Without d dot n, we can't do anything. So I would like to therefore make it clear by writing this particular statement. So then our next work will be, that means we are therefore immediately interested in learning how the electric and the displacement vector behave. So naturally you can understand what is our objective. Our objective is to understand how the electric field and displacement field will behave on the boundary. Either you can say on the boundary, or you can say at the interface of the two dielectric materials. Both are same at the interface of two dielectric material. Okay, why I am writing like this is that you should realize that there are two dielectric materials. That's what you have to realize. So how do you know where from two dielectric material is coming? We have been discussing only one dielectric, right? So that doubt will come. This point I already explained in the last class. So in order to demonstrate this, let me show this kind of a cube, which is a dielectric material. Okay, it can be of any shape, but I am choosing a cubical structure. And if you are going to have a dielectric medium like this, a particular single material, and consider the electric field inside the dielectric. Of course, this is going to be d vector, but I will write down electric field is there. You can always multiply by epsilon to get the d vector. I am talking about where is the surface. So you are able to see the boundary, right? So boundary of the material is, that is what you are seeing. Like that, you can have 6 of the faces. The 6 faces that you have for the cube, they are the boundaries. If it is irregular surface is there, that is also the boundary. So I am just showing the simpler situation where you can see the second dielectric material is the point that I am trying to explain. Let me finish this, otherwise this is another dielectric medium. Okay, so what I'm trying to explain is that I'm trying to explain where is the second material. The first material that you are going to consider is this dielectric material, which is going to have some epsilon as the electric permittivity for this material. So you are going to consider only single material. But what happens is, naturally, second dielectric material is automatically present, naturally present. So what is that is air. Because you are going to keep this dielectric material in the surrounding. So in the surrounding region, what is there is air is naturally present. So you are not going to evacuate. And the air happens to be a natural dielectric medium. And therefore, what happens is that you are going to get two dielectric material. That is what I am trying to explain. The two here. Okay. So where from the two dielectric material came, that's what I am telling. Even though you are taking a single dielectric material, the second material, which is air, is naturally present. And this material can be anything you consider. For example, glass. Okay, you can consider anything as an example. And I am just showing in some kind of green and blue color, but it's just a material made up of a single glass. In order to demonstrate three-dimensional view, I am giving some two different colors, and that's all about it. So the point is therefore clear that we are interested to know how the electric field, this particular electric field, will behave at the interface, that is at this particular point. So that is the statement that we are interested to calculate. Okay, so based on this, right now, what are the information that we have collected is, let me therefore write down the conclusions. So whatever we have done in the last, whatever the 2-3 classes, for example. So what are the major conclusions that we have is that we have calculated, or we have obtained the so-called surface charge density, which is represented by the sigma b, which is equal to the I would like to say what kind of charge density, B, right? B means what? So once again, bound. So I bound, better to write. Okay, I will come and write down. So P, okay, so this is actually a bound charge density. So let me insert here the bound. But the point I am trying to explain is this derivation we have done, but you should also be careful to know that there are two, the ways in which you can write down is identically same. It doesn't matter whether you put a prime here or not put a prime. That's what I'm trying to say. Because in some of the books you may find this kind of expression for the sigma bound. So you should not think that this is different. That's what I'm trying to explain. The polarization P is there, and the polarization is a function of R prime. That's what you're going to say. In this particular case, we simply say that it is a function of R. So the whether it is primed variable or unprimed variable, right now there is no problem, because after taking the dot product, all those vectors will disappear. Okay, so there is no problem whether you are going to consider the primed region or unprimed region. If you are going to have an appropriate diagram that we used to have in the beginning of the electrostatics course, in the very beginning, if you see the diagram, or in the multipole expansion diagram, any diagram, I always try to explain the difference between the primed variable and unprimed variable. So naturally, writing in the primed variable is in fact correct. This is how you are to write. Okay, so all the calculation are done in the primed variable. That means, what do you mean by that? The meaning is that the dielectrics contains what? Dipoles. So dipole is the source point, right? So because you are dealing with the source points, the variable has to be primed variable. That's all about it. And therefore, this is the way that you can properly write down. So this is the correct way I can say. But there is a point to be noted that this prime is not important when you are going to evaluate only a dot product. We are not going to perform a calculation with two variables, namely primed and unprimed. See, if you are going to do calculation with primed and unprimed, then only the distinction has to come very carefully. Right now we need only one expression, p dot n, and therefore for simplicity this expression is written as p dot n. So that point I would like to make clear, because in some of the books they may write like this, so you should not think that they are different. They are identically same. This is just a convenient way of writing down without the primes. That's all about it. So this is actually the bound charge density that I would like to say. And similarly, this is the first result that you have. And similarly, you have the next result, namely the volume bound charge density. So therefore I would like to write that the volume bound charge density is given by the negative of the divergence of the polarization. So once again, you can use the primed variable or unprimed variable. Unprimed variable is used for convenience, that's all about, but writing down in the primed variable is always nice. So both of them are identically same, whether you write in this style or that style, it's okay. And then coming to the bound charges, I would like to emphasize that they are the real charges that are present inside the material. The explanation I already told in the last class, they are real actually, not mathematical concept. Therefore, I would like to say that the bound charges are really present. Okay, really I want to emphasize. They are really present inside the dielectric. It may be zero or may not be zero. Okay, so that doesn't mean that it is always non-zero. It could be zero also, the value. So the point to be noted is that the bound charges are real. So the point is that it can be zero or it cannot be zero depending on the nature of polarization. See, usually what happens is when the polarization is uniform, surface charge density is not equal to zero. So these are some special cases. So I would like to write down that what happens is that the sigma b, the so-called surface charge density, is not zero, but the volume charge density will be zero. So when it is zero, a special case of polarization is uniform. So when the material is uniformly polarized, then this kind of special situation happens. Otherwise, everything is not equal to zero. So that's what I would like to say. So let me therefore write down that even if P is uniform. So what happens is sigma is not zero in any case. Only rho becomes zero in some special case where P is uniform. So this is a conclusion. This is important. And so I think these are how many conclusions are there. You can count. Okay, 1, 2, 3 is there. So this is the general situation where nothing is zero. Why I am writing this, why this is important is, when you're writing the examination like GATE and CSIR, you don't have to do lengthy calculation. 4 options will be given, right? When the polarization is non-uniform, then anything can be zero. Or if the polarization uniform, which one of the charge densities is zero? 4 options can be given. So such kind of questions, you don't have to do much calculation, but you can easily select the option if you know the basics like this. So that is the reason why I am taking some time and then writing here. So 1, 2, 3. So these are the results that we have. And let me also write down one more result, because we have discussed on the Maxwell equation, namely the Gauss law. So I would like to write down the next result, namely the Gauss law in dielectrics. So the fourth, right, this is 3. So 3 is over. Then the fourth one I would like to write down on the divergence of the electric field that you have is rho by epsilon naught is in vacuum. So this is in vacuum. So what will happen in the case of dielectric material? We have already derived it, and that is the expression given by divergence of D is rho free. So rho free is important, not just rho. And if you want to write down in the integral notation also, you can write down. So for the case of the vacuum, you have integral E dot ds will be equal to the Q enclosed. So enclosed is important. Enclosed means enclosed inside the Gaussian surface. And similarly, you can write down a corresponding equation for the dielectric. So for dielectric, I will write it in some kind of color here. So I'll write down the integral of the d dot ds. D dot ds will be equal to Q free. So this Q free is also enclosed. So we have to say that Q free enclosed. Okay, just I'm writing Q free. The understanding is Q free enclosed, like that. That is the meaning comes into picture. But the constitutive, this is called constitutive relation, D equal to epsilon E. This is very important. Every time you have to write down carefully, because in particular these expressions are valid only for linear dielectrics. So this emphasis has to be written down, or you have to write down. These relations are known as the constitutive relation, and the relation which you have written are valid only for linear homogeneous isotropic dielectric. Okay, that is very important. Otherwise, these expressions are not valid. So what is there in the right hand side is the corresponding to the material medium, and on the left side what you have is for the vacuum. So this is another conclusion that we have done it already, but we have not summarized. So now I am summarizing. And okay, so this is the, and what else is there? I think we can also write down something about the polarization. I have not written here, the constitutive relation. I would like to write down about the polarization. So it's coming to blue. So about the polarization, I have not written. So P is equal to, we write epsilon naught chi into E. So that will complete the constitutive relation. If these relations are not there, you can't evaluate the D vector. Okay, that is why we have to be careful in writing these constitutive relations. And then we will discuss, of course we have not derived this last one, but let me write down what is the energy stored in the electrostatic system. The reason why I am writing this is that the energy stored in electrostatic system is something that you study in BSc. So you are supposed to know this simple, of course, this simple expression. And now we can write down the corresponding expression for the case of dielectric. That's what I am trying to write down. So if you are going to represent the capital W is the work done. Work done is what is energy, right? So I will use the word capital W, probably I will write. So W will be equal to epsilon 0, or we say half epsilon 0 into the integral of the electric field square. Actually it is electric field square. It's not coming properly. Okay. Okay, so E square d omega. So this is the standard expression. The point I would like to tell you is, this is the expression which you must have derived in your BSc. And therefore, based on this expression, what we are planning to do is, we are going to write down the corresponding expression inside the dielectric. This expression is valid for vacuum. So that's what I am trying to write down. So here you write half into epsilon naught goes inside. So that becomes d dot E into a d omega, and it is for the entire omega. So it's clear that the E square is actually E dot E, that E dot E has become d dot E, because you can't write two times. If you write d dot D, what will happen? If both of them were D, what will happen is this will become epsilon naught square, isn't it? If this becomes square, then there is a trouble with the dimension. Dimension will not agree. Therefore, only one epsilon 0 should be there. So out of the two E here, E dot E, only one of them you convert to D. The another one you maintain that, so that the problem with the epsilon naught will not be there. So like this you can convert and write down. But if you are going to derive this completely from the beginning, you can always do that. Okay, so you have the proof like how to derive the expression for the energy stored in the electrostatic system in presence of dielectrics. So that is something that is at the base level it is generally studied. Therefore, I would like to give a comparison, so that as a part of overall discussion, this will be complete. And the rest of the thing is same, that you have d equal to epsilon E, etc., valid only for the linear medium. And then the one more point I would like to say is that the capital W, I have been using capital W for the work done, isn't it? So the work done, in the sense it is total energy. Okay, it's a kind of total energy. Assembling, we are not assembling anything. Okay, there's a total energy in the dielectric system, whatever electrostatic system in presence of dielectric. But generally what happens is, most of the time you may have to calculate the energy density. So energy density is a term that is important, and it is represented by the small letter. So the definition is very simple: total energy by total volume. That's all. So total energy is capital W and total volume is capital V. So that is what is represented by small letter u. So it is a standard. It is a standard notation. Small letter u, right? So this kind of small letter is a standard notation for the energy density. Density means total energy by volume. So you have to divide this entire expression by the total volume so that you get the energy density. So this is important because when you're trying to solve problem, okay, whether it is numerical problem or whatever it is, in problem solving, they will always ask you to evaluate the energy density rather than total energy. So therefore you have to be careful about this distinction. And so these are the major points that we have been discussing in the last few classes, and we have made the comparison between the vacuum case and on this side you have seen the case for the presence of dielectrics. So what is therefore next left out is that we have to derive an expression for the boundary condition for the electric field and the displacement vector at the interface of the two boundary at the interface of the two dielectric material. So that is the derivation that we have to do, and probably we will do that in the next class.